Is my slides visible to everyone? Hello.
Yes, sir.
Okay, thank you. So in the last class, we started looking at the uh, concept of pool boiling. We said that when we are boiling a particular liquid, there are different regimes we see. So initially, when the temperature is just above the saturation temperature and the degree of uh, excess temperature is around 2 degree, if the excess temperature is up to 2 degree, then mostly the evaporation is occurs from the uh, surface of the liquid, and it is called an interfacial evaporation regime. But if the degree of superheat goes beyond 2 to 35, then bubble starts forming, and between this B to D, when the degree of superheat is between 2 to 35, the regime is called as nucleate boiling. Again, further, this nucleate boiling regime is again divided into two sub regimes. So the first regime is B2C. In this regime, you can see that the degree of superheat is between 2 to 6. So here bubbles are formed at the surface, but even before these bubbles reach to the top surface, these get collapsed in the liquid. Okay, so stable bubble formation takes place only after point C. So from point C to D, stable bubble formation takes place, and these bubbles then rise vigorously through the liquid, adding the turbulence in the liquid, and because of that the heat transfer coefficient increases. So one can see that in a process application, one has to operate the process at nucleate boiling regime, because here you can get the advantage of higher heat transfer coefficient. Okay, but beyond the nucleate boiling regime, if you further increase the temperature, then what happens is the formation of the vapor film takes place around the surface, and this vapor film then add a additional resistance to the heat transfer, and because of that the heat transfer coefficient decreases. So from D to E, the formation of the film is unstable, so film appears and disappears, and because of that uh, uh, you can see that the transfer coefficient starts decreasing, and then it becomes the lowest at this point E to F, where the stable film formation takes place. Further, if we increase the degree of superheat, in that case you can see that the temperature of the surface is very high, and because of that the radiation heat transfer start dominating, and because of that the heat transfer coefficient further increases, and this regime from D to G is called as a film boiling regime. So in an industrial operation, we like to operate our equipments in nucleate boiling regime instead of operating them in a film boiling regime. So very often we are interested in finding this maximum value corresponding to D. What is the maximum value of heat flux corresponding to D? And this particular value is called as a critical heat flux. Okay. So typically we are interested to operate equipments between B to D, and more preferably between C and D. Okay. All right. So this is what we have seen in the last class. Then we said that in a nucleate boiling regime, when the bubbles are forming, whether these bubbles are going to be stable or not depends on the degree of superheat. Okay, so for that we started the derivation. So in this particular derivation, what we said that this is the Clausius-Clapeyron equation. In this Clausius-Clapeyron equation, we can integrate this Clausius-Clapeyron equation here. So as you can see that we are having a superheated liquid at the temperature of T1 and pressure of PL. Again, the saturation temperature of the liquid is Tsat. So clearly, whatever is the difference between T1 and Tsat, that is nothing but the degree of superheat. This degree of superheat is responsible for whether the formation of the bubble is going to be stable or not. So that decides whether the bubble is going to be stable or not. Okay. So let's assume that the if you take, let's say, a bubble like this, so pressure inside the bubble is, let's say, PV, pressure outside the bubble is, let's say, in the liquid it is PL, isn't it? So with this pressure PV inside the bubble, whether this bubble is going to be stable or not, that depends on how much is the difference between T1 and Tsat. So what is the degree of superheat that decides whether this particular vapor pressure PV is sufficient to make sure that this particular bubble is stable or not. Okay. So if the degree of superheat is lower, in that case, what happens is this bubble is going to get collapsed in the liquid itself. So we are trying to find out how much should be the size of the bubble in order to make it stable in the liquid. Okay. So we have integrated this particular equation between PL to PV. Isn't it? Here PV is nothing but the pressure inside the bubble. So that is the pressure, vapor pressure. PL is the liquid pressure. Okay. And we are integrating this dt by t square from Tsat to TL. So what we are trying to do here is how much should be the TL above the Tsat, which will make this PV, value sufficient to keep this particular bubble stable in the liquid. That's what we are trying to calculate here. Okay, so that's why we have integrated this dlnp between PL to PV, whereas this dt by t square we have integrated between Tsat to TL. So after integration, what we get is ln PV by PL is equals to LV by R 1 by Tsat minus 1 by TL. Here LV is nothing but the latent heat of vaporization and R is the universal gas constant. Okay, this equation we can rearrange further. So ln PV by PL we can represent like this, isn't it? So 1 minus, so you can, rearrange this term and you will get PV by PL itself, isn't it? So again, ln 1 plus PV by PL, PV minus PL by PL, this can be further approximated using this Taylor series expansion. So here you can see that ln 1 plus x we can approximately take as x itself, isn't it? So that's what we have done here. So ln 1 plus PV minus PL by PL, this can be approximated as just PV minus PL by PL. And right hand side again we can rearrange. So after rearranging we get LV by R TL minus Tsat divided by TL into Tsat. After rearranging, again PV by PL, PV minus PL by PL, this particular term PV minus PL can be represented using the Young-Laplace equation. So Young-Laplace equation gives 2 sigma by R. That's what we have seen in the previous slide, isn't it? PV minus PL is nothing but 2 sigma by R, where sigma is nothing but the surface tension. Okay. So if we put this particular equation in this original equation, what we get is TL minus Tsat is 2 sigma R TL into Tsat divided by R rho L LV. Here this capital R is the universal gas constant, whereas the small r is the radius of the bubble which will be stable in the liquid. Okay, again, so TL and Tsat. So remember, very often the degree of superheat is not very high. So for instance, the TL is, let's say, 100 degrees Celsius, isn't it? Sorry, Tsat is the 100 degrees Celsius for the water at 1 atmospheric pressure, isn't it? So degree of superheat, let's say 10 degree we are having. So TL into Tsat will be what? TL will be 100 plus 273 plus, let's say, 15 degree is the degree of superheat, isn't it? And Tsat will be just 373. So you can see that the magnitude of TL and Tsat is very high compared to the degree of superheat, and therefore this TL into Tsat you can approximately take as Tsat square without worrying too much. Okay, so that is the another approximation used here. So with this approximation, then our equation becomes simplified. TL minus Tsat is given as 2 sigma R Tsat square divided by R rho L RPL LV. So here from this equation you can calculate the radius R, which can be, so you can calculate radius R of the bubble, which will remain stable for the given degree of superheat. That's what you are trying to find out. So you can pinpointedly calculate what will be the radius of the bubble which required in order to keep it stable in the liquid, in the superheated liquid. Okay. So if the bubbles are having the radius less than this R value, then all such bubbles are going to get collapsed in the liquid. That's what it is. So radius higher than this will be the stable bubble. Other than if the bubbles radius are lower than this R value, then these are going to get collapsed. Okay, is it clear to everyone? Hello, this is what we have seen until last class. Is it clear?
Yes, sir.
So what we are trying to say here, again I'm repeating, what we are trying to say here is, for the given degree of superheat, what should be the size of the bubble to keep it stable in the liquid? That we are calculating from this equation. That we are calculating. Okay. So again, take the simple calculation to appreciate the concept. If we take the water, let's assume that there is a 10 degree superheat at the atmospheric pressure. We wanted to find out what should be the size of the bubble, the stable bubble in the liquid. That's what we are trying to find out for this given 10 degree superheat. So 10 degree superheat means T1 will be 110, Tsat will be 100 degrees Celsius. Again, we are looking at the atmospheric pressure, so PL will be 1.013 bar. Surface tension of the water we can obtain directly from the table which is given backside in the book. So surface tension of the water is 0.063 Newton per meter. Latent heat of vaporization is 4.07 into 10 raised to power 4 kilojoule per kg per mole, and universal gas constant is 8.314. If you put all these values in this particular equation, and we can back calculate this value of R. So we can put all the values here. TL minus Tsat is nothing but the degree of superheat, that is already given as 10 degree. And we can put all the values except this R, and we can back calculate the value of R. So R comes out to be 3.55 into 10 raised to the power minus 6 meter. So this is nothing but 3.55 micrometer, isn't it? So what information we are getting from this calculation? The information which we are getting from this calculation is, if the size of the bubble is less than 3.55 micrometer, all such bubbles will get collapsed in the liquid. Only the bubbles having the size more than this 3.55 micrometer will remain stable in the liquid. That's what we are calculating. Is it clear to everyone?
Sir, but R calculated is 3.55 into 10 raised power minus 6. So how can be a bubble greater than for this particular temperature?
So this is the critical limit, isn't it? This is the critical limit. So when we are saying that the size higher than that means what? The vapor pressure will be higher than the liquid. That means bubble will remain the stable. Remember, the bubble is going to collapse in the liquid only if the liquid pressure is higher than a particular limit, isn't it? Remember this equation?
Okay, sir, I got it.
Isn't it? So if my size of the bubble is less than that, in that case you will see that the PL is higher than what you are calculating from this equation. So that means this bubble is going to get collapsed.
Sir, I want to say that let's say R be the critical radius, RC be the critical radius, and there be a radius greater than, let R naught be the radius greater than RC. So when we keep R naught here, we have to change like PV inside the vapor pressure inside the bubble.
That's what I'm saying. So if PV is higher than this critical value, doesn't matter. Still my bubble will remain stable, isn't it? Because see, what is the situation? Everywhere there is a liquid, isn't it? Everywhere there is a liquid. Let's say I am having a bubble here. So if my bubble inside pressure inside this bubble is higher than this value, doesn't matter, isn't it? The only problem comes when this PV is the vapor pressure here is smaller than this critical value. In that case, what will happen is this liquid pressure and this effect of this surface tension will make this bubble collapse. Is it clear?
Yes, sir. Yes, sir, it is clear.
Discard. Okay, so that is what we have calculated. Okay. So clearly now let's look at, so we started with the concept of boiling. We started with the concept of boiling. We have discussed several regimes in the boiling profile, isn't it? Then we started looking at the concept of nucleation, isn't it? Because we wanted to know what size of the bubbles will be stable in the liquid. Okay. And now we are looking at how we can calculate the heat transfer coefficient. So again, continuing with the same idea of calculating the heat transfer coefficient using the correlation. That's what we are trying to look at. Okay. Again, as I said previously that in the process application, we wanted to keep our boiling regime at nucleate boiling regime, isn't it? We wanted to maintain the boiling at nucleate boiling regime. Why? Because we are going to get the higher heat transfer coefficient in that regime, isn't it? That's what we have said, isn't it? If we maintain our boiling in this particular nucleate boiling regime, then we can have the advantage of higher value of heat transfer coefficient, isn't it? Correct? Do you all agree?
Yes.
So typically, if you look at the process applications which are used for the boiling, generally we have several tubes, and these tubes are packed into a shell. So the liquid then vaporizes in the tube or even in the shell. Okay. So that's what in general the equipment is used, and this type of arrangement is called as a shell and tube heat exchanger. We will look at more details on this later when we will see the heat transfer equipments. But for a time being, the heat transfer equipment used for boiling is very often it is a shell and tube type, where the liquid either flows through the shell or through the tubes. Okay. Again, these tubes can be arranged in horizontal manner or a vertical tube, doesn't matter depending on what type of equipment you are using. And typically the boiling depends on several things, several factors like boiling surface. It depends on the rho, that is nothing but the density. Cp is specific heat, thermal conductivity K, viscosity, and surface tension and excess temperature. These are the different variables on which the boiling basically depends on. So out of these, all these factors, the parameter like boiling surface is very difficult to quantify, because it depends on whether your surface is rough, smooth. All sort of things can be possible, isn't it? Sometimes there will be a fouling on the surface, isn't it? So this is very difficult to quantify. So typically the correlation used for boiling is this Roshenau correlation. So this Roshenau correlation gives the heat flux QS as mu L LV in the bracket G rho L minus rho V by sigma, where sigma is nothing but the surface tension. So rho L is nothing but the density of the liquid, rho V is the density of vapor, and this entire bracket raised to the power 1 by 2 into CPL into T divided by CSF LV Prandtl number raised to the power n, and this entire bracket raised to the power 3. Here CPL is nothing but the specific heat of the liquid. T is nothing but the excess temperature. CSF and N are the constant that depends on what type of surfaces you are and liquid combinations you are using. For instance, if you are taking water and stainless steel, in that case CSF is 0.013 and the exponent N is 1. Again, LV is the latent heat of vaporization and PRL is nothing but the Prandtl number of liquid. So this is the most commonly used correlation, Roshenau correlation. This is used for nucleate boiling. So these correlations are given for nucleate boiling. For nucleate boiling, the correlation used is a Roshenau correlation. Okay. Another correlation, slightly simpler correlation compared to the Roshenau correlation, is given by Mostinsky, and this correlation gives the heat transfer coefficient directly. Again, this is if you compare both these correlations, a more accurate one is the Roshenau, whereas easier to calculate is Mostinsky. So Mostinsky has given the heat transfer coefficient, boiling heat transfer coefficient in a nucleate boiling. It is related to the critical pressure, reduced pressure, and excess temperature. So this is the equation is given, and these properties, critical pressure, reduced pressure, that you can directly obtain from the properties of gases. Okay. Isn't it? So very often, properties of the gases are tabulated. So you can look at the different books like Properties of Gases by Prosnitz and Reed. You can get these values, critical pressure and reduced pressure, etc. So you can find out critical pressure and reduced pressure, and the excess temperature is very often is given. So if you put in this equation, you can calculate what will be the heat transfer coefficient, boiling heat transfer coefficient. Again, this heat transfer coefficient will not be as accurate as you obtain from the Roshenau correlation. Okay, is it clear to everyone?
Sir, more accurate is Roshenau.
Roshenau, yes. More accurate is Roshenau, but easier one to calculate is Mostinsky. So remember this QS you can represent in terms of the you can represent HA delta T, and you can still calculate H here directly, isn't it? Here H is directly given. Is it clear?
Yes, sir.
Remember this QS will be what? QS will be what? Boiling heat transfer coefficient multiplied by temperature difference, isn't it? Correct. So H you can directly calculate here. So H will be what? HB will be given as this entire equation divided by A into delta T, this entire equation divided by delta T.
Sir, how one gets, how Rosenau was able to get this much complicated equation?
So okay, just a minute, I will explain. So this QS we can write as H into T, H into T, excess temperature. Excess temperature is the difference, isn't it? Okay, how Roshenau got? So remember in the last two chapters, forced convection and natural convection, how we have developed the correlation? Can you recall the procedure?
By sort of.
Okay, I don't worry. So what we do first? We first find out what are the different parameters which are important in the given system. So these are the different parameters which are important. Correct? This is the first step. How we get which parameters are important? These are based on the experiments. When we perform several experiments, we find out that what are the different parameters which are important. So in the boiling, these are the parameters which are important. Among these, this boiling surface we can exclude because this is difficult to quantify. It's difficult to quantify. This we have excluded. So the other parameters, then we can use the dimensional analysis. We can use dimensional analysis. Okay, we can use the dimensional analysis, and dimensional analysis can give us what are the different dimensionless factors. Those are important for quantifying the particular system. Do you all agree? Yes or no?
Yes, sir.
That is the second step. What is the third step? The third step is, once we find out what are the different parameters, those are important. The next step is then perform experiments. Perform experiments by varying these parameters, isn't it? And then develop the correlation in terms of the dimensionless groups, isn't it? Is it clear? That's what we do, right? So same procedure Roshenau has also implemented. He first found out what are the different parameters, those are important. Based on that, he found out what are the different dimensionless parameters which are important in this case, and based on that, then he generated the data, and that data he fitted into this particular equation, And this particular equation he has given as a correlation for nucleate boiling. Is it clear? Is it clear to you now?
Yes, sir.
So this is the standard procedure. Remember all these correlations which are developed or used in heat transfer calculation. All these correlations are having the same basis. The way we are doing it here. Okay, correct. Now you can ask me that this other correlation is slightly different, isn't it? So this is not based on the same principle which is used here. Remember there is another principle, like if you remember in the last class we have said that Prandtl analogy and Chiltern analogy, that those analogies we have used for finding the heat transfer coefficient, isn't it? You remember? Isn't it? So some people also develop the correlation based on these analogies. So these things are, this correlation is primarily coming from that type of analysis and not the dimensional analysis which we are looking at here. Is it clear? Does it make sense now? Hello?
Yes, sir.
Your yes is lacking that confidence.
No, sir, I got it now.
Got it. Okay. So say it confidently if you got it. Otherwise, we can discuss further.
Yes, sir, I got it. It's clear now. No issue.
Okay. All right. Thank you. All right. So far we were saying about the nucleate boiling. But remember what we said? Nucleate boiling, we wanted to find out the heat transfer coefficient, but very often we wanted to check. We wanted to check whether our obtained heat flux is beyond this critical heat flux or not. That we wanted to check, isn't it? We wanted to make sure that our equipment operates in the nucleate boiling regime, isn't it? If I'm operating in a film boiling regime, then I'm losing a lot of money, isn't it? Because I am having a very high excess temperature and I'm not getting a very high heat transfer coefficient, isn't it? So I need to operate only in the nucleate boiling regime. So for that I need to check whether the current boiling operation is falling in the nucleate boiling regime or not. So how we can do that? We have to first calculate the critical flux, isn't it? So see this equation, you can apply this equation and find out QS. But whether this QS is actually from the nucleate boiling regime or not, you will not be sure, isn't it? You have been given the excess temperature, all these properties you can find out at the saturation temperature, and you can calculate QS. But whether this QS is actually falling in a nucleate boiling regime or not, that checking is very much required. Because otherwise, see, these are the correlations. These are the correlations given for nucleate boiling. But let's say this T is corresponding to, let's say, film boiling. You can still calculate QS by assuming that T, isn't it? But whether this QS is actually from the nucleate boiling regime or not, that you may not be sure, isn't it? So in order to make sure that whatever the QS you are calculating is less than the nucleate boiling, is less than the critical value of the heat flux, there are correlations given for the critical heat flux as well. Is it clear to everyone? Yes or no?
Yes, sir.
So see, I again try to explain it. So this figure is given to you. That's why you are pinpointedly able to say that this is the onset of film boiling beyond which I should not go. Between D and B I should work. This is because you have looked at this entire boiling curve. But when you are operating your equipment, this entire boiling curve is not available to you. You will be given only one TE value. One TE value will be given to you. This boiling curve is not available to you, isn't it? So only a single TE value is given. Now with that single TE value, you can calculate QS. You will get the QS. But this QS will be a correct QS only if the corresponding TE is in the nucleate boiling regime, isn't it? Otherwise not. Otherwise this is just the equation, isn't it? Whatever the value of T you put it will give you some output. Whether this QS is the correct one or not, that you will not be able to know, isn't it? So for that, one additional checking is required. And that additional checking is in terms of finding the maximum value of Q, which is nothing but the critical value of Q, isn't it? So this critical value of Q, which is nothing but Q max, you can calculate using another correlation which is given by Zubair. Is it clear to everyone? Is it clear to everyone what we are doing and why we are doing? Why we are doing is more important.
Sir, can't we check the value we got of Q through experiment and compare it with what we got from the equation keeping T?
Okay. So see, you are saying that let's calculate this QS. Let's calculate this QS using this equation. And let's calculate the Q value experimentally. That's what you are saying?
Yes, sir, yes, sir. And comparing the two, we will be getting to know
Absolutely.
it is nuclear boiling or not.
You are correct in that. But very often we design the boiling experiment even before the experimental setup is ready. Remember, all these EPC companies do what? They design all these boilers and everything a priori, isn't it? Before constructing the plant. So that experimental value is not available to you, isn't it?
Okay,
you are using this calculation in order to design. Remember, your objective is to find out what value of TE you need to maintain in your boiler. What value of TE you wanted to maintain in your boiler, isn't it? So some value of TE you have selected, and based on that you have calculated the QS, but you are not sure whether that QS is falling in actually in a nuclear boiling regime or not. That you can only confirm by checking this Qmax. Correct? Is it clear? Does it make sense what I'm trying to say?
Yes.
So all the analysis people do even before the construction of the equipment, isn't it? When you are designing the boiler, all these calculations you are going to do a priori, isn't it? And then you are going to construct your boiler. So ultimately, when you are constructing your boiler, how much TE you wanted to maintain between the liquid and the superheat liquid and the saturation temperature, this you need to figure out a priori, isn't it? Correct.
Sir, so is it like first we calculate the Qmax, and if the QS is less than Qmax, then T is correct?
Then T is correct. That's what we are
saying. Sir, yes, but absolutely. What if the liquid is lying in the AB regime?
What is the liquid?
Lying in the AB regime, like that. It is just starting boiling.
So here this entire curve I have shown here is for water, but it is not required. Very often, you might work with some other liquid, maybe acetone, maybe some other liquid, isn't it? But this curve I have shown for water. So that's why even this value of here we are saying, isn't it, between 2 and 35 I am going to get the nuclear boiling. That is true only for water, not for some other liquid. In fact, we will see one example solved on such thing in order to appreciate the concept a little bit more. Does it make sense? Is that you were asking?
Sir, I was asking, like, the boiling thing, what if that lies in AB? Like every
okay. How we are going to make sure that whether it is lying between AB. Yeah. Okay, all right. So see, this AB regime is very small. This AB regime is a very small, isn't it? It's up to 2 degrees, isn't it? 2 degrees superheat. So very often you will see that the degree of superheat, you often keep it beyond this. You don't use with a very small degree of superheat up to 1 to 2, isn't it? So that anyway, this particular regime anyway you will exclude easily, because very often you will see that the excess temperature is around 5 or 10 or even more than that, isn't it? So higher limit is more critical than the lower limit. Lower limit anyway you will not keep 2 degrees, isn't it? It will be slightly higher than that. Does it make sense? So this can be excluded easily, because anyway, see, this is 0. That means the temperature is exactly same as the saturation temperature. And if you are maintaining, no matter what liquid you are keeping, if you are maintaining only just 1 or 2 degree superheat, that's not a good idea, isn't it? So that option you can, eliminate easily, because you are starting from the higher value and you try to keep it somewhere here. You try to keep your operation somewhere here, so that some tolerance is there, and also you are having a reasonably higher value of HB.
Okay, sir.
Is it clear?
Yes, sir.
Okay, another thing to exclude here is, you can see that in this regime, another way of excluding this is log SB is linearly proportional to T. Got the point? If your heat transfer coefficient is coming out to be linearly proportional to T, you just assume that that's interfacial evaporation. But people generally don't do that, because this lower limit, see, typically you don't use 2 or 3. You use always, more than 5, 6. Okay, so this anyway get excluded in that. Does it make sense? Somebody asked the question.
Yes, sir.
Hello? Hello?
Yes, sir.
All right. Okay.
Sir,
Please go ahead.
Sir, this AB and BF will have same slope. Like when we do cooling from F, it will merge to E with in a straight line.
You are saying AB and
Sir,
E.
when we do cooling from F side, it comes to be straight. So
No,
I am saying that
some slight variation in the slope will be there. I have just drawn it like this, but it may not be. Okay.
yes. Only that was the confusion.
I have just tried to show it pictorially that it is not going to follow the same boiling path while cooling. That's what I just wanted to say, because this metastable state, this state will continue as a metastable state for some more temperature decrease. Okay, that's what I'm trying to say here. All right. Okay. These are some of the correlation. There is another correlation given by Sun Linhard on calculating this Qmax. This slightly more complicated correlation. This is for a horizontal cylinder, heat flux in a horizontal cylinder. So here we are first calculating Qmax by assuming the infinite horizontal plate, and that then is used in this particular equation to calculate the actual Qmax. Okay. All right. Some more correlations are given here. Again, the correlation given by Bromley for horizontal tubes, but these correlations are for film boiling. These are the correlations for film boiling. Okay, remember here we are talking about the critical heat flux. Here we are talking about the correlations for nucleate boiling. Okay, but this last one is a heat transfer coefficient for a film boiling. Okay, so very often even the calculation of the heat transfer in a film boiling is also important. Okay, when the temperature is very high, then when the radiation becoming dominating, in that case it's a film boiling, isn't it? So the heat transfer coefficient can be calculated using this equation. Also, very often what people do is they calculate the radiation heat transfer separately. They also calculate the HB using this particular formula, and then they combine to calculate the overall heat transfer coefficient. All right. So let's not spend too much time on these correlations. These you can go through. These are just the equations. Let's move to the examples, then you will appreciate the concept. Okay. Okay, so consider a nuclear boiling of ethyl acetate at 1 atmospheric pressure. If the superheat in the liquid is 5 degrees Celsius, so TE is given, that is 5 degrees Celsius. Calculate the diameter of the cavity on the boiling surface which produce a bubble nucleus that does not collapse after release from the surface. That is part A. In part B, what we are looking at, if a cavity has a radius of 1 micrometer, what degree of superheat is necessary so that the bubble nucleus grows in size after detachment from the cavity. Okay, so let's look at the part A. In the part A, we wanted to find out the diameter of cavity. So we are interested in finding out the R value. This TL minus Tsat is already given, that is 5 degrees Celsius. We can calculate all other properties for ethyl acetate based on the temperature. So all the properties has to be calculated at the saturation temperature. So let's first look at the saturation temperature for the ethyl acetate. So ethyl acetate has the saturation temperature of 350 degrees Celsius, 350 Kelvin at 1 atmospheric pressure. So 350 plus this degree of superheat 5, that gives me the liquid temperature TL, which is 82 degrees Celsius. Also, we can calculate the liquid pressure and the surface tension. So these two correlations are used. These correlations are given in the properties of liquid and gases by Prosnitz and Rees. Okay, so this first equation is an Antony equation. So this Antony equation relates how the liquid pressure is going to be related with the temperature. That is what is correlated here. So here theta is nothing but the temperature in degrees Celsius and PL is nothing but the liquid pressure. Again, here we have used log. So it's a log to the base 10. Okay, so now in this case we know the value of theta. Theta is already given as 82 degrees Celsius. We can put it 82 here and we can calculate PL. So PL comes out to be 1.189 bar. Okay, similarly from the second equation we can put theta here and we can calculate sigma, which is nothing but the surface tension, and the surface tension then we have converted into a Newton per meter. So 1.68 into 10 raised to power minus 2 Newton per meter is the value of surface tension. The latent heat of vaporization for acetone is given as 3.3605 into 10 raised to power 7 joule per kg per mole, and the universal gas constant is 0.08314 meter cube bar per kg per kilomole Kelvin. Okay, so now we can put all these values in this equation and we can calculate the value of R. So that's what we have done. We have put all the values here and we have back calculated the value of R. So R comes out to be 1.713 into 10 raised to power minus 6 meter. So that means what? If the cavity radius of the cavity is 1.713 micrometer and above, then only the stable bubble formation takes place and the bubble will not collapse in the liquid. That's what we are trying to prove here. Now the second part is, in the second part, this cavity radius is already given. The cavity radius is given as 1 micrometer. And the question is, how much degree of superheat required to have the bubble stable for this particular value? We are asking a reverse question. We are asking the reverse question that this R is given. What value of TL minus Tsat is required in order to have this given R as a stable R? That is what we are asking in the second part. Is it clear? Problem is clear to everyone?
Yes, sir.
Okay. So,
Sir,
please go ahead. So what I'm trying to say is, in part B, we have been given the radius of the bubble and we wanted to find out what will be the degree of superheat required in order to maintain that bubble stable in the liquid. So this R is given as 1 micrometer, isn't it? So what should be the minimum value of degree of superheat that required in order to maintain this R value stable in the liquid? That's what we are trying to find out in part B. So this R is given, we wanted to find out TL minus Tsat. Is it clear to everyone?
Yes. But the last line says that the bubble nucleus grows in size after detachment from the cavity.
So that happens because once the bubble is formed in the cavity, several bubbles coalesce as they move up, and therefore the size of the bubble increases. Okay. So what it means is if I don't make the bubbles of this size, if I make the bubbles of lower than this size, then even before they coalesce, they are going to get absorbed in the liquid itself. That's what I'm trying to say. They are not going to coalesce with other bubbles at all. Okay.
Yes, sir.
Okay. Okay. So in this case, now this PL and this sigma, which is nothing but surface tension, these are not known. Why? Because we are having only these equations, and this TL is unknown, isn't it? Remember, in this case, this theta is nothing but what? This theta is nothing but a temperature in C, isn't it? But this temperature we are not knowing. We don't know the temperature TL, isn't it? We don't know the temperature TL. So this theta will be what? TL minus 273, isn't it? Then and then only we will get the temperature in degrees Celsius. So that's why this theta is replaced by TL minus 273. TL minus 273. That's what we have done here. Okay. So in this equation, this PL is now we have represented in terms of TL. Similarly, this surface tension sigma also we have represented in terms of TL, and this TL is unknown. Okay, now let's put it in this equation. So TL minus Tsat, this is again unknown. So Tsat is known. So Tsat we are putting 350. TL minus 350 will be the left hand side. Right hand side, this part will be what? 2 into this sigma, which is in terms of TL minus 273. Into R, which is given, into 350 saturation temperature square, divided by R value is given 1 micrometer, so that is 10 raised to minus 6, into LV is also given, latent heat of vaporization, that is 3.3605 into 10 raised to power 7. And this PL we can calculate from this first equation. So we can calculate PL as, this is given as log base 10. So PL will be given by 10 exponential of this entire bracket. So that's what we have represented here. Now in this entire equation, both left hand side and right hand side, the only unknown is TL. So we can use a trial and error here and we can calculate the TL. So TL comes out to be 358. So 358 minus 350 I do, then I get the degree of superheat as 8. So what we are trying to say here is, if we maintain the degree of superheat equals to 8 degree, then this 1 micrometer bubble is going to remain the stable in that. But if the degree of superheat is less than that, then this bubble is going to get collapsed. So one can see here is that as the degree of superheat increases, the size of the bubble which can remain stable in the liquid decreases, isn't it? So when we had the 5 degree superheat, then we got the size as 1.73. So slightly higher size is required, isn't it? But when my degree of superheat is increased from 5 to 8, then the critical value is just 1 micrometer. Can you see? Is it clear? Does it make sense to everyone what I'm trying to say? Hello? What happened? Am I audible?
Yes, sir. Yes, sir.
Okay. So I am actually looking at my white screen, so I don't get to know whether I am audible or not. Okay, so you just have to tell me in between. All right. Okay, so let's look at another problem. So in this problem, what is been given is calculate the rate of boiling. Calculate the rate of boiling of water in a 0.35 meter diameter stainless steel pan. So this is circular pan is there. Okay. At 1 atmospheric pressure, if the bottom of the pan is maintained at 115 degrees Celsius. So what we are trying to find out, calculate the rate of boiling of water in a 0.35 meter diameter stainless steel pan at 1 atmospheric pressure. Okay. So here the water is given. So boiling point of the water is 100 degrees Celsius, but the pan temperature is maintained at 115 degrees Celsius. So degree of superheat is 15 degrees Celsius. isn't it? So let's calculate all other properties of the water at saturation temperature of 100 degrees Celsius. So that these are given again from the tables which are there in the book. So viscosity, specific heat, density, latent heat of vaporization, surface tension, and Prandtl number all are taken from the table which are given at the back side of the book. So these are the values. So viscosity is 2.79 into 10 raised to power minus 4 Newton second per meter square. Specific heat is 4.22 kilojoule per kg per degree Celsius. Density is 958 kg per meter cube. Latent heat of vaporization is 2257 kilojoule per kg. Surface tension is 0.059 Newton per meter. And Prandtl number is 1.76. Again, for saturated steam, this is for a liquid water. For a saturated steam, the density is given as 0.5955 kg per meter cube. In this case, we are using a stainless steel and the liquid is water. So for stainless steel and water, as we have discussed earlier, for stainless steel and water, CSF is 0.013 and the exponent is 1. So that is what we have taken directly. And these are also given for a different combination of the material and the liquid. These are given in the book, table number 6.1. Okay. So now, as I said that in this case, first let's assume that it's a nuclear boiling regime, isn't it? We don't know whether it's a nuclear boiling regime or not. Just by looking at the temperature of 50 degrees Celsius, we are assuming that it's a nuclear boiling regime. This temperature 15 degrees Celsius is definitely higher than 2 degree or 3 degrees. So this interfacial evaporation that we can neglect that possibility, isn't that? We can eliminate that possibility safely, isn't it? So whether this is a nuclear boiling or film boiling, that we don't know it. Just by looking at the temperature, it looks like it's a nuclear boiling, but we are not sure whether it's a nuclear boiling or not, isn't it? So let's calculate the heat flux. So heat flux is calculated here using Roshenau correlation. So this is the Roshenau correlation. So all values we know: mu L, LV, G, rho L, rho V, sigma, CPL, TE, CSF, LV, PRL. Everything is known in this equation. We can put everything and we can calculate QS. So QS comes out to be 462.5 kilowatt per meter square. So this is with the assumption that the system is in a nuclear boiling regime. We don't know it. So what we have to do after this? What we have to do? Anyone?
Calculate Qmax.
Calculate Qmax. Correct. So that's what we have done here now. So again, we have calculated the Qmax here. Qmax, we have used the Joubert correlation. All the properties we know. So those properties values we have put it in this equation and we have calculated Qmax. So Qmax comes out to be 1259. So clearly this QS is much lower than this Qmax. We can say safely we can say that we are falling in a nuclear boiling regime. Do you agree? Do you all agree?
Yes, sir.
Yes, sir. Yes, sir.
Then what is the question? Question is we have to calculate the rate of boiling. Rate of boiling is what? Rate of boiling is nothing but how much kg of the water is boiling per second. That is what is called as rate of boiling. We got this QS. QS is nothing but 462.5 kilowatt per meter square, isn't it? If I divide this QS by latent heat of vaporization, what I'm going to get? If I divide this by latent heat of vaporization, what I'm going to get? I'm going to get 0.205 kg per meter square second. This is what we have obtained. And if I multiply this value by area of the pan is given, isn't it? Stainless steel pan at with this 0.35 meter diameter. So if I multiply this by area, I get the rate of boiling in kg per second, isn't it? So this area of the pan is pi by 4 d square we have calculated. We have multiplied this area to this rate here, and we got the rate of total rate of boiling as 0.01972 kg per second. We can convert this into an hour, so that comes out to be 71 kilogram per hour. Is it clear to everyone? Hello?
Yes, sir.
Yes, sir.
So when we are saying rate of boiling is kg per second or kg per hour. Don't get confused with rate of boiling. When we are saying, don't get confused with rate of heat transfer. Don't get confused. This only one word is missing. Rate of heat transfer in boiling, that is a different meaning, and rate of boiling has a different meaning. Okay, is it clear? Is it clear to everyone? We are habitual of looking at this rate word, frequently in this course. So we often get confused with rate of, heating. So don't get confused. Rate of boiling is nothing but kg per hour. Kg per hour of water that is going to get boiled over the surface. All right. So as I said, this Roshenau correlation and Joubert correlation we have used just to again, check what type of values we can get using Mostinsky correlation. So we have just used the Mostinsky correlation. So this is the excess temperature we know. From this excess temperature, we can calculate the, the given pressure is 1 atmospheric pressure. So for this given atmospheric pressure, we can look at the properties of the water, and we can see there that the critical pressure is 221.2 bar, and reduced pressure is nothing but what? The actual pressure divided by critical pressure, so that we can calculate PR as this, isn't it? We can put both these values here. This excess temperature is already given. We can calculate HB. HB comes out to be 22 kilowatt per meter square degree Celsius. Again, HB into excess temperature will give me QS. So HB into TE gives me 330 kilowatt per meter square. And this value are, close. They are not very, far different, isn't it?
Sir, I have a doubt.
Please go ahead.
Sir, what if on applying the correlation, we get Qmax, we get Q as less than Qmax, but we are operating in the film boiling regime, the transition regime. So that can also be a possibility, right? So how do we conclude that?
Acha, so okay. You are saying that we can get
after
QS.
the critical heat flux in the
No,
DE
so
region.
see, okay. So Roshenau correlation is only given for this regime.
Yeah, that's what, right? So what if we apply, what if we are operating in the DE region, but we apply the Roshenau before?
So in that, so see, okay. So if you apply the Roshenau correlation in this regime, this QS value will be very high. It will not come like this.
Okay.
So that's a correlation, because see, at this region, your TE value will be very high.
Right. Got it.
So that will give you a QS value higher. This, see, Roshenau correlation will keep on giving. This Roshenau correlation will keep on going the increased value with T like this.
Got it, sir. Yes.
Isn't it? It will not give this value.
Right.
Is it clear?
Right. Yes, sir. Clear.
Okay. So we can see that the Mostinsky correlation also gives a reasonably close value. So see, very often, the properties of a particular liquid are not known. In that case, it is better to use this Mostinsky correlation because it is easy to apply. Only you require is what? You don't require anything. You require only, see, pressure is given to you. Based on that pressure, you can find out what is the critical pressure for that particular liquid. And that critical pressure, once you know, then you don't require anything. Isn't it? Actual pressure divided by critical pressure gives you a reduced pressure. Critical pressure you already know. Excess temperature also you already know. You can calculate HB directly. This will not be very accurate, but it is very easy to calculate. You don't require so many properties to calculate. See, here you require so many properties. Isn't it? Very often all these properties are not known. Can you see the point? Hello? Hello? Does it make sense to everyone?
Yes, sir.
Okay. Okay, let's move to, so far we were only looking at the boiling. We were looking at the, the boiling in which we were not adding any turbulence by using the mechanical elements. So we were only looking at pool boiling. Now let's look at the forced convection boiling. So in a pool boiling, whatever the turbulence was caused in the liquid, that is primarily because of the movement of the bubbles because of the density difference. Okay, but in a forced boiling, forced convection boiling, what we do is we pump a subcooled liquid through a channel like this. This channel walls are at a higher temperature TW, and what happens is in this particular channel, this subcooled liquid is then converted to vapor by boiling. Okay, so initially you can see that this subcooled liquid, since this walls are at a higher temperature, you can see that the bubbles start forming at the wall. So initially there is a subcooled boiling takes place here. Subcooled boiling is what? Subcooled boiling is a regime in which the bubbles get collapsed in the liquid itself. But as we move further, you will see that these bubbles, more and more bubbles starts forming, and that particular regime is called as a bubbly boiling. Then in the next, if you further move up, you can see that these bubbles coalesce and the more bubbles starts forming, and these bubbles then move together at the top, and this type of regime is called as a slug flow. If you further move up, what you will see that only the liquid films will be there at the surface of the wall, whereas the vapor will be flowing through the annular place, annular channel. So this entire channel will have a vapor, whereas the liquid will remain only at the wall here. So this type of regime is called as an annular flow regime. And if you further go up, you will see that there is a mist flow. So that means only the liquid droplets and the gas is moving up. Okay, so here you can see all these small things are the liquid droplets. Okay, and the other thing are nothing but gas. Is it clear? So this happens when you are pumping a subcooled liquid to a heated channel like this, and this type of boiling is called as a forced convection boiling. Why we are calling it as a forced convection? Because a mechanical element is used to pump the liquid through the channel. That's why it is called as forced convection boiling. Is it clear to everyone? Hello?
Sir?
Please go ahead.
In annular flow, these two pure liquid are like stationary. The film is stationary.
No. Film will form and this will change this shape, isn't it? Because what happens here is the gas is there, gas is moving up, but the liquid, so see here the liquid mist is going, isn't it? So which is kind of condensing at the surfaces here, even though the surface is higher at a higher temperature, but these are because see, heterogeneous condensation is offered at the wall, so you will have a thin liquid film occurring at the wall here. But if you move further up, this film also will evaporate here. So you can see there is no film here because of higher temperature of the wall. Is it clear?
Oh, sir. Okay.
So this is called as a forced convection boiling. Again, there are a lot of correlations and lot of intricate details are associated with that, but we will not go through that. We will not go through that. Okay. So as per the boiling is concerned, we will stop here. Okay, please go ahead.
Sir, till the mist flow, there is the presence of water. Above that, it is completely vapor, single phase vapor flow.
Yes. Then single phase vapor. Yes. So there are, see how many phases are there? Subcooled boiling, bubbly boiling, slug flow, then annular flow, mist flow, and single phase vapor flow. So 1, 2, 3, 4, 5, 6 stages are there. Okay. Please go ahead.
So the only difference is like we are pumping the liquid in it.
So only difference here is we are pumping the liquid, and this type of boiling you will, it's not that we are looking at the hypothetical case. In fact, this type of boiling regime you will see in nuclear plants. Nuclear power plants primarily have this type of boiling regime. So this is very important. You know, this system is very important. This is regularly used in the nuclear reactors,
So
nuclear power plants.
is it like jacket hitting or a different thing?
So see what happens in the nuclear power plants. Remember, these you know, wall will be hit by the energy, nuclear energy eliminated, nuclear energy generated, isn't it? And then that has to be transferred to the heavy water, isn't it?
Yes.
And the heavy water then heated the liquid water later, isn't it? That is what is used. So what was the question? Sorry, you were saying something. Please go ahead. Hello. Is there any question?
Sir,
Please
will
go ahead.
this apparatus be kept horizontally or vertically, or anyway is fine?
Both possibilities are there. So we are looking at the horizontal case, but there are both possibilities are there. And in fact, in a horizontal case, see, even in the horizontal case, this type of things can occur, isn't it? Because the flow is now not because of the buoyancy. Flow is because of the mechanical force added by the pump here, isn't it? Yes or no?
Yes, sir. Yes, sir.
So this is possible even for the horizontal case, doesn't matter. Of course, this will not look so orderly the way it is shown here, isn't it? All right.
Yes, sir. Yes, sir.
Okay, all right. So far we were only looking at the boiling, concept of boiling. Let's now extend our discussion to condensation. Okay. Remember, the chapter name is boiling and condensation. Okay, so boiling we have looked at so far. Let's look at condensation. So condensation means the change of phase from vapor to liquid, and it's very you know, often used in the process application. Okay, so whenever we are having the mixture of vapor and gas, and the temperature is lowered below the saturation temperature, what happens is the gas, the vapor starts forming the small tiny liquid droplets, and this is called as a condensation. And these are suspended in the carrier gas. So this type of, you know, condensation is called as a homogeneous condensation. Why we are calling it as a homogeneous condensation? Because the droplet formation taking place in the vapor itself. Okay, that's why we are calling it as a homogeneous condensation. There is another type of condensation which is called as a surface condensation or a heterogeneous condensation. What happens is, in the heterogeneous or a surface condensation, the vapor comes in the contact of the cool surface, and the droplet starts forming on the surface, the solid surface. Okay. And this type of condensation is called as a surface condensation. So if the condensation, again there are two more, you know, classifications are there. The first one is a film condensation and the another one is a drop wise condensation. So film condensation is what? So very often what happens is, whenever in a heterogeneous condensation or a surface condensation, whenever the vapor comes in contact with the cool surface, what happens is, the vapor starts condensing on the surface, and eventually what happens is the entire surface is wetted by the liquid. A thin film is formed, and that thin film starts you know, moving in a downward direction. So that type of condensation is called as a film condensation. So film condensation occurs only when the liquid wets the surface. This word is very important. So wetting of the surface takes place. So here you can see that this is the film condensation. So this is the gas, this is the vapor which comes in the contact of the cool surface, and because of that a film of the liquid forms and which moves in a downward direction. But in contrast to this, there is another type of condensation which is called as a drop wise condensation. So in the drop wise condensation, what happens is, this vapor comes in the contact of the cool surface, and because of that different drops are formed. But these different drops do not coalesce with each other to form a film. Why? Because In this case, what happens is the surface properties of this cool surface are such that there is no wetting of the surface which takes place by the liquid. So the surface is not wetted by the condensate and drops. So because of that, these drops do not tends to coalesce and form the film. Rather, they stay in the form of drops itself. And since these stay in the forms of the drops itself, you can see that some of the areas of this surface comes in a direct contact with the vapor, and because of that the resistance to heat transfer is lower here, and therefore drop wise condensation in general gives you a higher heat transfer coefficient compared to the film wise condensation. Because in a film wise condensation, you can see that this particular liquid film then act as a resistance for the heat transfer, and because of that the heat transfer coefficient is lower in a film wise condensation compared to the drop wise condensation. But the problem is drop wise condensation requires contamination or a modification of the surface, which may not be desirable in a actual operation. And because of that, the most practical application of the condensation usually falls into this film wise condensation regime rather than drop wise condensation. Drop wise condensation requires surface modification by adding surfactants, etc., which may contaminate your liquid, and you don't want it to have that. And because of that, even though the drop wise condensation gives you almost 7 times more heat transfer coefficient compared to the film wise condensation, usually the film wise condensation is used instead of a drop wise condensation. Is it clear to everyone?
So can you repeat? I didn't get the point why it is used.
Okay, so see, drop wise condensation gives a higher heat transfer coefficient, almost 7 times heat transfer coefficient than a film wise condensation. Why? Because some of the areas of this surface are directly exposed to the vapor, and therefore there is no resistance present here in this region, isn't it? In contrast with this, if you look at the film wise condensation, entire film is wetted by a liquid, isn't it? And entire surface is wetted by the liquid film, and this liquid film offers the additional resistance to the heat transfer. Therefore, the heat transfer coefficient is lower here. You are clear up to this?
Yes, sir. Yes, sir.
Now the question is, one can argue that when the drop-wise condensation is giving a more heat transfer coefficient, then one should use a drop-wise condensation. Why people in general use the film-wise condensation, isn't it?
Yes, sir. Yes, sir.
But the problem is the drop-wise condensation requires surface modification. When you will have a formation of such drops and not a film, you will have a formation of such a drops and not a film only if
when it is not wetting.
If the liquid is not wetting the surface. So wetting of the liquid is not there, and this can be ensured only by adding the surfactants on the surface or oil on the surface. Then and then only you can have that type of that type of phenomena will be seen only in that case, isn't it? So that means what? You need to add some surfactants on the surface. That means what? You are contaminating the surface. If you add a surfactants and at the surface, that means this liquid also will get contaminated by a surfactant, isn't it?
Sir, can't we take the original boundary of the
original? Okay, original surface. So very often you see that what type of material is used. Very often stainless steel is used, isn't it? Because the temperatures could be very high. Stainless steel or even some metal surfaces are used, isn't it? Unlike some modified surfaces. So the choices of a surface itself giving a drop-wise condensation, that choices are very few. You got the point?
Yeah, yes, sir. Yes, sir.
So because you also need to maintain a particular temperature also, isn't it? So you need to have a material which can withstand that much temperature, isn't it? So strength, temperature, the ability of the material to withstand the temperature, all these factors are also important, which may not always, will be in your favor in addition to naturally obtaining this type of condensation. Correct? Does it make sense?
Yes. Yes,
So
sir.
that's why very often you see only a film wise condensation. You don't see a drop wise condensation. Also see another aspect of film wise condensation and drop wise condensation is, in a drop wise condensation the condensation has to occur slowly. You need to give a larger surface area, isn't it? You got the point? Larger surface area, because see here each of these drops are forming, then each of these drops will coalesce and one line will drip down, isn't it? So the condensation
It will have low
rate will be very low. Correct?
for film one.
For a drop wise condensation rate will be condensation rate. I'm saying, I'm not saying heat transfer. I'm saying condensation rate will be low in a drop wise.
Okay, I got it.
Isn't it? Very often you wanted to cool down everything quickly. Isn't it? You don't want it to wait for a longer time. So that can be possible only in a film wise condensation. You can have a lower heat transfer gradient. The temperature difference you can maintain the way you want it. Doesn't matter. Here the temperature difference has to be maintained slightly close to the temperature of the surface should be slightly lower than this vapor surface. And then only the drop wise condensation will take place. Correct?
Yes, sir.
So all these factors, because of all these factors, the mostly preferred condensation regime is this film wise condensation rather than a drop wise condensation, even though a transfer coefficient is higher here. All right.
Sir, is it like we are choosing to have film wise condensation because it is better that there is no condensation at all, right?
So we are choosing a film wise condensation. That is, you are absolutely correct in that, because that facilitated several other things. Isn't it? If we use the drop wise condensation, we are restricted by several things. Restricted by several things means we need to have a particular surface. Then we cannot have a very high condensation rate. Condensation rate is what? The kg of fluid condensed per unit time. We will have a limited condensation rate in this case. Here we can have a higher condensation rate in a film wise condensation, even though the rate of heat transfer doesn't matter, isn't it? I can have a higher temperature difference here. I can have a higher temperature difference in order to get rid of this resistance. But at least then I will have a higher rate of condensation instead of getting. So see, I will suffer in terms of the heat transfer. It's okay, but the time is also important here, isn't it?
Yes, sir.
Sir, is it like this that we want more condensation rate because the more the condensed liquid will be formed, the heat of that would be offered to the remaining amount of vapor, and that would lead to increase in the heat transfer coefficient.
No. Heat transfer coefficient is okay. So don't get confused. What I'm trying, so see, don't get confused here. I am saying the heat transfer rate here in film wise condensation is lower compared to drop wise. But when we are saying the condensation rate, transfer rate and condensation rate both are different. Condensation rate is nothing but the amount of liquid condensed per unit time, kg per hour. So you can see that the condensation rate will be higher in a film wise condensation compared to the drop wise condensation, even though the rate of heat transfer is lower in film wise condensation compared to the drop wise condensation. You got the point?
Sir, I got this, but my question is why we want more condensation rate, like
so
why
see,
we are choosing.
Okay. Why we are wanted to have a more condensation. So see, in a process operation, let's say the distillation column you are looking at. Distillation column you are looking at, you are taking the vapor out from the top surfaces and you wanted to condense it. You wanted to wait for an hour or you wanted to get it done as quickly as possible.
Okay, sir. Got it.
Got the point? So if you use the drop wise condensation, it is going to take more time. So you wanted to wait for a more time there, or you wanted to cool down as quickly as, because that cooled liquid will be used as a reflux later, isn't it? That will be
Yes, sir.
used
Yes,
as a
sir.
reflux in the distillation
Yeah.
column.
Yeah.
So if you wait for more time, then you are suffering in terms of the purity in a way, because your reflux rate will not be that much.
Yes, sir. Yes, sir.
So very often, see, it's not about the heat transfer. Very often we are also interested in the rate of condensation. Rate of condensation is a very important factor. You want it to cool down as quickly as possible, isn't it? You don't want it to wait for an hour or 2 hour or 3 hour, isn't it? If you are getting the entire vapor condensed in half an hour, that itself is a a reasonable thing to look at. Instead of waiting for 2 hours in a drop wise condensation, even though you will get a very effective heat transfer there, but are you ready to wait? Got the point?
Yes, sir.
That conviction is missing. Still not convinced?
So this higher
No, sir.
heat
No, sir.
What? Somebody was saying.
higher heat transfer won't say that the mass would also be higher.
No, not at all, not at all. Higher heat transfer rate means what? Higher heat transfer rate will be nothing but what? Heat transfer coefficient will be more. But here you are, trying to make these individual drops. You got the point? And these individual drops, and you need to have a larger surface. Then and then only you will have enough surface to form individual drops. In this case, you will have a smaller surface, isn't it? So your instrument will be compact. So basically the amount of vapor condensed per unit time for a given same area is higher in a film wise condensation compared to a drop wise condensation. Let's say if you use area constant in both the cases, then more will be the amount of material condensed in a film wise condensation compared to the drop wise condensation, isn't it? Provided that you give a higher temperature difference here, doesn't matter, isn't it? Make sense? Hello?
Yes.
So you can readily have a higher temperature difference. There is no problem in that, isn't it? But here, even though if you had a higher temperature difference, eventually what will happen? Eventually it will form a, okay. So okay. Maybe I give you another interesting example. So if you look at even a film wise condensation, if you do not put a high temperature difference initially, the starting of the film wise condensation is also similar to a drop wise condensation. But as you increase the temperature difference between this wall and this vapor, then what happens is most of these bubbles coalesce and then eventually forms a film. Okay. So that means what? The higher flow rate, whenever you wanted to get the higher flow rate of the condensate, you are in a way breaking the drop wise condensation to film wise condensation. Make sense? Still not clear? Hello?
Yes, sir. It's clear.
Maybe I just try to explain again. So let's say this is the surface. This is the surface. If my temperature difference at this surface, let's say vapor temperature is, let's say T1 and the wall temperature is, let's say T0. Wall temperature is T0. So initially, if this T1 difference between this T1 and so this T0 is smaller than T1, then and then only the condensation is taking place, isn't it? So if this T0 is lower than T1, in that case, what will happen is initially such drops will be formed. Okay. Difference in the temperature is not very high. But as you increase the difference between T1 and T0, that means you lower this T1 further, lower this T1. In that case, what happens is these drops will coalesce with each other and eventually this entire thing will become a film. Can you see the point? Is it clear?
Yes, sir.
So starting of the film wise condensation is also a drop wise. But then if you increase the
Coalesce.
increase the coalescence because of more condensation. Eventually you will get a film wise. Can we move, or is there any question? Hello? Hello?
No question, sir.
Try to imagine. If you imagine, then and then only you will appreciate what. Okay. So how much time we have? It's already. Okay. So I think one more tutorial is there on the same topic. So I will give a brief, description on this, but we will cover this entire thing again in the next class. Okay. But I'm trying to give you a brief on this so that, we can do the tutorial in this week. Okay, so what we are trying to do here is we are trying to quantify a film wise condensation. So we are assuming that a stable film is formed, okay, like this. So here the direction of X is from top to down, and the direction of Y is in a horizontal direction, which is shown here. So now in order to quantify the condensation, hello?
The screen is not your slides are not visible.
My slides are not visible. Okay, sorry. So it is not visible just now, or it was from a long time?
Just now.
Just now. Okay. Is it visible now?
Yes, sir.
Okay, so we are trying to quantify the film wise condensation. So we are assuming if a stable film is formed like this condensation film, the thickness of the condensation film is delta X. The direction of X is from top to down. So this direction of X is this and direction of Y is this, isn't it? So at a particular X, at a particular value of X from the top, the thickness of the film is delta X. Thickness of this film is delta X. Again, to quantify the entire thing, we are assuming a shell of thickness delta X. This is the shell we are assuming. This shell is having the thickness delta X. This shell is located at the distance X from the top and distance Y from this left hand side wall. Okay, so this distance is wall and this distance here is X. Okay, again, the thickness of this element is delta minus Y. So thickness of this entire film here is del X, and del X minus Y, this distance is Y. So this del minus Y is nothing but the thickness of this element. What we are assuming that the condensate film is in a fully developed laminar flow with zero interfacial shear. So the shear at this interface of the film and the vapor is zero. We are assuming the constant liquid properties. So we are assuming the constant liquid properties, and the temperature here is the saturation temperature. This temperature is the liquid temperature is a saturation temperature. The temperature of the wall is TW. The vapor is saturated. We are assuming that the vapor which is present here is a saturated vapor. We are also assuming that heat transfer through the condensate film occurs by conduction only, and the temperature profile is in the film is linear. So we are assuming that this film is there which is laminar, but we are only considering that the conduction is taking place here. So heat transfer is taking place only by a conduction. That's what we are assuming here. So that means the temperature profile is going to be linear. So temperature profile is linear only when this thickness of the film is also not changing, isn't it? Remember, when the cross-sectional area changes, I don't get the linear profile, isn't it? So we are assuming that the thickness of the film is not changing too much. It's not changing drastically, and because of that, the temperature profile is linear. That's what we are assuming. Also, the film is assumed to be very wide. So film is in the Z direction, which is perpendicular to the plane of your laptop. So in that direction, the film is infinite. We are assuming a infinite film in a Z direction. But that width we are considering as a unit width. So this contradiction is there. So contract don't get confused with that, what we are doing is we are calculating everything per unit width in a z direction. That's why we are referring it as a unit width. Is it clear to everyone? All the rates we are going to calculate per unit width. So that's why unit width we are considering, even though that width is very large. So the wall effect we are neglecting in a z direction. That's what we are trying to,
Yeah, means like no ends are there nearby this portion.
Correct.
In the
That's
Z.
why we are saying the infinite width is there, but all the calculation you will see that these are per unit width. So that width we are considering as a unit width in a z direction. Z direction is what? Which is perpendicular to the plane of your laptop. Does it make
Okay,
sense,
sir.
everyone?
Yes.
All the assumptions are clear to everyone. Why we are making even this this third assumption is very important, because we are only assuming that the conduction. Remember, even in the laminar flow, convection can take place, isn't it?
Yes,
Isn't
sir.
it? But we are neglecting that. We are assuming only, we are basically what we are doing is we are assuming that this film itself is very small film in terms of width, and it remains almost stagnant, and because of that only the conduction is taking place, and the thickness of this film is not changing too much. That means cross sectional area is also not changing too much, and because of that the temperature profile is linear. That's what we are assuming everywhere. Is it clear, everyone? Hello?
Yes, sir.
Okay. Now there are two problems we have to solve first. First we have to, so see, there are two things are there. Remember, if we are starting from this leading edge, the thickness of this film will start increasing, isn't it? Even initially the thickness is 0, but eventually this film moves down, more and more vapor is condensing, and because of that the thickness will increase, isn't it? So this delta x is a function of x. That is why it is a function of x, because as we move from the top to down, this delta value is going to increase. Correct. So in this particular case, there are two things to look at. First is I wanted to find out the what is the velocity profile here. Okay, what is the velocity profile at a particular x, and that velocity profile, remember in this case that velocity profile, then I can multiply to the cross sectional area and multiply to the density. I will get a mass flow rate, isn't it? And that mass flow rate is then related to, so remember how much amount of mass added in the film is directly related to how much amount of vapor is condensed, isn't it? So the mass flow rate, which I am going to get it from the velocity profile, has a direct relation with the heat transfer. Can you see the point? Does it make sense what I'm trying to say?
Yes, sir.
So mass flow rate, so first here we are calculating the velocity profile. Velocity profile will give me, if I multiply to a area, I will get the volumetric flow rate. Volumetric flow rate, if I multiply to density, I will get the mass flow rate. Again from the heat transfer is what? Heat transfer in this case is what? Mass into the latent heat of vaporization. The amount of heat transfer here I have obtained is mass into latent heat of vaporization, isn't it? So I can directly obtain the mass from this heat transfer, and also I am getting a mass flow rate here. So more the mass is added because of condensation, higher will be the mass flow rate.
Sir, we are getting mass flow rate using the heat, the amount of heat flowing.
Yes. So both are, we can we can obtain both, and we can compare, we can equate both these things, and we can calculate what will be the width of this film at a particular location. That is what we are trying to do here. Okay, so initially we are only looking at the velocity profile, how my velocity profile is going to be at this element. So this element we have assumed, this element is at a distance x from the top, and it is at the distance y from this left hand side. So in order to calculate the velocity profile, what we have to do is we have to make the force balance. So what are the different forces acting on this? there is a shear force which is acting in a upward direction. So F1 is a shear force, and then F2 is the weight of this mass, this element which is acting in a downward direction, and there is a buoyancy force F3 which is acting in a upward direction. Okay, so the force balance in this case is the shear force F1 will be equals to F2 minus F3. So that is what we have put here. So shear force is given by again Newton's law of viscosity. So that is mu into du by dy, that is the shear stress. And the shear stress I multiply by area. So area will be what? Area will be what? In this case, this is moving downward direction, isn't it? This film is moving, so this element is also moving in a downward direction. So what will be the area? Cross-sectional area from the top. So cross-sectional area from the top means what? Y multiplied by Z, isn't it? So what is acting in this case? So okay, so cross-sectional area, okay, shear force will be acting on this direction, isn't it? This direction. So
dx,
what will be the area? Dx into dz. Dx into dz will be there, isn't it? Dx into z, sorry, not z, dz. It will be z. Correct?
Means with W.
So z is there in the perpendicular direction. So mu into du by dy into dx into z. So dx into z will be the area which is acting on this surface here, which is responsible for the shear resistance. Correct? Yes or no?
Yes, sir. Yes, sir.
So that z is multiplied here. Now this is balanced by what? F2. F2 is what? F2 is the gravity. So gravity will be what? Rho L is nothing but the density of the liquid into G is nothing but the acceleration due to gravity multiplied by volume you have to do. So what will be the volume of this particular element? Delta minus Y into dx is the area and into Z is required. That will give you a volume, isn't it? Correct? So Z should be there, isn't it? Similarly, the buoyancy force which is acting upward will be given by what? Rho V into Z delta minus Y into dx into Z. So all these terms will have a Z term, and those Z terms I have eliminated. Can you see? Is it clear?
Sure.
So dx into Z you will have on the left hand side. Here this first term will also have dx into Z. So dx into Z into delta minus Y, that will give you a volume of this element. That volume of the element is multiplied by density is going to give you mass of this element. Mass of this element multiplied by G is going to be the force acting, isn't it? Similarly this. So that Z I have eliminated from all these three terms. That's why I have not written Z here, Z here and Z here. Okay, clear?
Yes, sir.
Okay, sorry. So if you put it here in this equation and rearrange everything, what you are going to get is mu L du by dy dx is equals to rho L minus rho V G delta minus Y dx. And if you rearrange everything and integrate, what you are going to get is the velocity u. Velocity u is given as, so this is the velocity of what? Velocity of the liquid flowing in the film. This liquid is flowing in a downward direction, isn't it? So u rho L minus rho V G UL, and this integration of this term will be what? Delta y minus y square by 2 plus c. Can you see? This is rearranging. UL I have taken it on this right hand side. So that becomes rho L minus rho V by mu L into G, and this integration of delta minus y into this dy here I can take, isn't it? This dx will get cancelled out. So dy I will get it on the right hand side here, isn't it? So this becomes y into delta minus y square 2 plus c, and du we can integrate that to u, isn't it? Can you see the point? This equation, is it clear? Hello? Okay, I think let us stop here.
Yes, sir. Dx will cancel and then we have integrated this. Yes.
So let us stop here. We will continue from this point. I wanted to at least cover this so that we can do the tutorial, but doesn't matter. We will do the tutorial. No issues. Okay. Can we stop here? Sorry for extending little bit. Okay. Hello, is it okay?
Yes, sir.
Okay, so let us stop here. We will continue from this point onward.